Welcome back, students. We're going to continue with our discussion here of electrochemistry. Many of you may have done this experiment in an earlier chemistry course. A copper wire is placed in a solution of silver nitrate. Initially, the solution is colorless, but after some time, the solution begins to turn aqua blue. At the same time, the wire becomes covered with a set of crystals, a crystalline deposit of silver. If we look at the process at the atomic level, what is happening is the copper metal atoms are losing electrons and becoming copper 2 ions. This is what gives the blue color to the solution. The electrons released by the copper as it oxidizes go and reduce the silver ions in solution, turning them into silver metal, which deposits in the forms of crystals on top of the original copper wire. Eventually, all of the copper will be oxidized to copper 2 ions, and the majority of the silver ions in solution, which were in excess to start with, will become silver crystals. Now, this is a reaction that happens in a beaker. But it should occur to you that, is there any way we could use that transfer of electrons in a productive way? This is what is called an electrochemical process. It's a process that consists of an oxidation-reduction reaction in which either the energy released by the spontaneous reaction is converted to electricity, or alternatively, we use electrical energy to cause an otherwise non-spontaneous reaction to occur. You should all probably review in your memory what we talked about spontaneous and non-spontaneous reactions in the previous unit and realize or remember that a spontaneous reaction proceeds with the release of free energy. In other words, energy available for productive work. Let's consider a reaction similar to the one we just talked about. But in this case, I'm going to submerge a bar of shiny zinc metal into a solution of copper 2 sulfate. In this case, the zinc is going to oxidize into zinc ions, and the electrons released in the process are going to cause the copper 2 ions to become reduced to copper metal. What we would observe is that the zinc begins to get covered with this deposit of dark material, and at the same time the solution, which was bluish to start with, starts losing its color. As you see, the reaction proceeds because electrons are transferred from the zinc to the copper 2 ions. What if there was a way that I could put a barrier in between these two and have the two reactions happen in separate compartments? As a result, what would happen is that now, for the electrons to be transferred from the zinc metal to the copper 2 ions, I'm going to have to produce or put in some kind of a circuit. And of course, once I put this circuit through which these electrons are traveling, voila, what I have is electricity. The simple way of doing this is by creating what is called a galvanic cell, also called a Voltaic cell. We're going to watch a video where they describe how this is constructed and the different parts of it, and then we're going to come back to our PowerPoint.
When a strip of zinc metal is immersed in an aqueous copper 2 sulfate solution, electrons are transferred from zinc to the copper 2 ions. Copper metal deposits on the zinc strip and collects at the bottom of the flask. Zinc atoms are oxidized to zinc 2 ions, which enter the solution. This spontaneous oxidation-reduction reaction is summarized in the chemical equation shown. The spontaneous copper-zinc oxidation-reduction reaction can be made to yield useful electrical work by incorporating it in a voltaic cell. The zinc electrode is immersed in a solution of zinc sulfate. The copper electrode is immersed in a solution of copper 2 sulfate. No current flows through the light bulb because the electrical circuit is not complete. To complete the electrical circuit, we add a tubular bridge filled with aqueous sodium sulfate solution with a porous plug on each end. We now have a complete circuit and current flows. When we replace the light bulb with a voltmeter, we find that the cell has a potential or voltage of 1.1 volts. The copper electrode is the positive electrode, and the zinc electrode is the negative electrode. As the cell reaction proceeds, zinc atoms of the zinc electrode lose electrons and move into the solution as zinc ions. At the same time, copper-2 ions acquire electrons at the copper electrode and form copper metal. The reaction in the left-hand compartment is oxidation of zinc. The electrode at which oxidation occurs is called the anode. The reaction in the right-hand compartment is reduction of copper. The electrode at which reduction occurs is called the cathode. Electrons flow from the anode to the cathode through the external circuit. To maintain electrical neutrality in the two cell compartments, ions must move through the salt bridge. In summary, remember that in a voltaic cell, the anode at which oxidation occurs is the negative electrode. The cathode at which reduction occurs is the positive electrode. Electrons flow through the external circuit from anode to cathode.
So this diagram that you see here is similar to the one shown in the video. The only difference in this case is that you can see the salt bridge is made of potassium chloride instead of sodium sulfate. The actual components of the salt bridge are really not that important. The important thing is to supply ions to make up the difference as our different electrodes become oxidized or reduced. On the left side, we see the bar of zinc submerged in a zinc ion solution. And in the zoom view there on the left of the atoms, you can see how zinc atoms are getting oxidized and electrons are being released and essentially transferred along the surface of the metal towards the circuit that goes on the outside. Zinc is oxidized at this electrode, and we call this electrode the anode. Electrons travel through the circuit. Of course, as they travel, that electrical current can be used to, in this case, for example, turn on a light bulb. But they're going to arrive at the other electrode where they're going to cause copper-2 ions in solution to become reduced into copper metal. In this case, because we've provided a copper cathode, a piece of metal, the atoms of copper that are formed are able to deposit in the proper metallic crystal structure. So we don't see that dark, messy stuff that we saw when we carried this reaction in a beaker. At the cathode, copper-2 ions are getting reduced, and reduction is what is happening here. At the bottom of your screen, you can see the two half reactions. On the left for the oxidation of zinc, on the right for the reduction of copper-2 ions. If you want a quick way of remembering which electrode is which, just think alphabetically. A of anode before C of cathode, O of oxygen before R of reduction. And that way you can remember. Don't forget that as zinc ions are being produced in the anode, they could offset the balance of that solution, which is why the salt bridge provides some negatively charged ions to neutralize the zinc ions being produced. At the same time, at the cathode, as copper-2 ions are removed, to eliminate the risk of a short circuit, we provide potassium ions, in this case from the salt bridge, to continue neutralizing the solution. If we combine both of these half reactions now, we have a spontaneous redox reaction. And you can see the full equation there in the bottom. Now remember, we're looking for an electrochemical process. In this case, in this construct that we're calling a galvanic or sometimes voltaic cell. So what we'd like to do is find out, well, what is the potential for generating work? In other words, how much electricity can we get out of this? So if instead of a light bulb, as in the video they demonstrated in the video, you put a voltmeter, you can read that there's a voltage in here between the two half cells, right? Remember, potential means that two items are in positions where there is a tendency for them to interact in favor of or against a fundamental force. In this case, it's the force of attraction between negative and positive sides. And that potential represents a, a sense of, how chemically close these things are to generate a reaction that will produce energy. The difference in the electrical potential between the anode and cathode has different names in these kinds of galvanic or voltaic cells. We can call it the cell voltage, we can call it the electromotive force or EMF, or we can simply call it the cell potential. And we will use those terms interchangeably. Most of the time, I'll talk about the cell voltage or the cell potential. Those are perhaps my favorite ways of saying it. Okay, let's consider again the equation here. As usual, scientists like to simplify things or make diagrams that represent things that are otherwise very difficult to represent. Like, for example, it would be really cumbersome to try to draw these beakers and these wires and this voltmeter every time I want to talk about this cell. So instead of that, what I'm going to do is I'm going to set up some conditions. I'm going to set the solutions of the ions at 1 molar concentrations, and I'm going to draw what is called a cell diagram. And a cell diagram looks somewhat like this. I have deliberately colored the two sides of the full cell just to highlight the differences, but you don't have to do it that way. You also don't need to write the words anode and cathode. Once you understand how a diagram works, you'll be able to tell which one's which. So by convention, we're going to write the equation at the anode on the left side. Notice that we had to indicate that we start with zinc metal, that is solid, being converted into zinc ions in a 1 molar concentration solution. That's what the left side of the diagram demonstrates. And notice that it's written in the same order as the reaction happens from left to right and oxidation at the anode. At the right side, we can see what happens at the cathode. And once more, we write it in the order in which it happens from left to right. From copper 2 ions, we have a solution that's 1 molar being converted into copper metal. That's a reduction reaction. Notice that in a cell diagram, it is important to write down what the physical states are, because as we'll see later, we're sometimes going to incorporate substances that are gases, right? Or even solutions that are not going to be 1 molar. Notice that there's several vertical bars here. You see these two here to indicate a phase boundary. In the case of these items, the boundary is between the solid electrode and the solution of ions. We also have in the middle a double bar, and that indicates the salt bridge. Notice that it is not necessary to indicate what are the components of the salt bridge. The double bar by itself tells us what it's going to be. Now, the next question we ask is, if we put a voltmeter, it says that there is a potential of 1.10 volts here. That is the potential to generate electrical energy. How do we get that number? In your PowerPoint notes, we're going to take a little tour here through some slides. Unfortunately, some of these slides did not make it into your PowerPoint notes version, so you will have to take some notes as we go along, and I apologize for that. We're going to start by defining what is called a standard reduction potential. And we represent it by a capital E, right, an uppercase E with a superscript of 0, so E naught. This is the voltage associated with a reduction reaction at 1 electrode when solutes are in 1 molar concentrations and gases are at 1 atmosphere of pressure. Very important. The standard reduction potential is always given for the reduction reaction. So for example, although in the previous cell we had zinc metal being oxidized to zinc ions, if we want to find the standard reduction potential, we will do it for the reverse of that. In other words, the reduction of zinc ions to give me zinc metal. Notice that if we do it for something like chlorine gas, we have to indicate the physical state and the pressure. And then as you can see, the products, chloride ions, are in aqueous solution at 1 molar. Like I said, you have to indicate the conditions here. The standard reduction potential for the reduction of zinc ions is negative 0.76 volts. And for the reduction of chlorine gas, it's 1.36 volts. Obviously, the question you're going to ask is, how do we obtain these values? Well, just like we did in thermodynamics, we're going to start up by setting a standard or a reference. We're going to set up a reference electrode. This electrode is called the standard hydrogen electrode, or SHE. Notice that it's essentially a solution of 1 molar HCl into which is placed a platinum electrode. Of course, platinum is inert, and hydrogen gas is pumped in at 1 atmosphere of pressure. Let's look at the reduction reaction in this case. The reduction here consists of hydrogen ions, of course, that's from the acid solution that's being dissociated, getting electrons to form hydrogen gas, and the hydrogen gas is at 1 atmosphere. What we're going to say is that the standard reduction potential, the E naught, for this reaction is 0 volts. It sounds arbitrary, but remember, this is a reference electrode. This is very similar to when we were doing enthalpies or heats of reactions, and we decided that the enthalpy of formation of a given element in its most stable state was going to be 0. So we're just arbitrarily setting up what our 0 is. Hey guys, we do this all the time, right? How do we run the Celsius scale of temperature? We have arbitrarily set 0 Celsius to be the freezing point of water. It's kind of like a choice we made as a reference for other temperatures. Okay, so step number 2 is we're going to assemble a Voltaic cell. But in this case, we're going to test our substance of interest against the standard hydrogen electrode, SHE. If I set up this cell that I show in here, if you look at it, you can draw a cell diagram that looks like this. Please take a look at it. Notice the double bar in the middle indicating the salt bridge that separates the anode on the left from the cathode on the right. The anode, I have zinc metal being converted into zinc ions in a 1 molar solution. Notice that the cathode consists of the standard hydrogen electrode where hydrogen ions at 1 molar are being converted into hydrogen gas at 1 atmosphere pressure. And we're adding the platinum in there to indicate that there is the presence of this solid electrode here. We typically need some kind of a solid surface for electrons to be able to be transferred into whatever the receiving substance is. Okay, now let's consider the half reactions in this cell. Okay, here's our cell. Here is the cell diagram. And we have, first of all, at the anode, we have oxidation. And oxidation consists of zinc being converted into zinc ions at 1 molar concentration with the release of 2 electrons. At the anode, what we would have is the reverse of the reduction reaction, right? If we reverse this equation, we would get the reduction of zinc ions to become zinc. And that is the equation for which we're trying to find the value of the standard reduction potential. Remember, the standard reduction potential is always given for the reduction direction. Regardless of what happens at the electrode, we want to find the potential for the reduction reaction. That's the one we're trying to find. We don't know what it is. Let's consider again our cell and let's see what is happening. Remember, at the anode, what you have is an oxidation. So technically what you would have here is, let's call it like a potential for oxidation. But remember, because oxidation is the reverse of the reduction, that means that this would be the negative of the reduction potential for zinc. So the potential at the anode is the negative of the actual standard reduction potential. Now let's look at what's happening at the cathode. At the cathode, you're having electrons come in to reduce hydrogen ions at 1 molar concentration to produce hydrogen gas at 1 atmosphere. Now, the reduction potential here would be the reduction potential for the conversion of hydrogen ions into hydrogen gas. That is exactly what the standard hydrogen electrode is, right? So let's consider now the two half reactions and let's add them up. As you can see, the electrons are going to cancel out, and so we end up with the sum of these two reactions, giving us zinc metal reacting with hydrogen ions to produce zinc ions and hydrogen gas. Now, because we're adding the two half reactions, therefore the potential of the cell would be the potential of both electrodes. We have something that we've called the potential for oxidation of the anode and the potential for reduction of the cathode. But remember that what we've called the quote-unquote oxidation potential is actually the negative of the reduction potential for zinc ions. Therefore, we can say that at the anode, we're going to consider the negative of whatever the reduction potential is at that electrode. For the reduction part, we have hydrogen ions being converted to hydrogen, so that gives us the potential at the cathode. Now, what do we see in this process? We see, therefore, that since we have the potential at the cathode plus minus the potential at the anode, the equation therefore becomes the potential for this cell equals the potential of the cathode minus the potential at the anode. Now let's plug in some values. We know that the cell here is reading a voltage of 0.76 volts. And we know that the potential at the cathode, that being the hydrogen electrode, should be 0. So essentially what we're saying is that 0.76 volts is 0 minus whatever the standard reduction potential is for zinc. In other words, once we solve the equation, we get that the standard reduction potential for zinc is minus 0.76 volts. In other words, the standard reduction potential for this equation, the conversion of zinc ions to zinc, is negative 0.76 volts. That's how we arrived at that value for zinc of minus 0.76. Okay, let's repeat the experiment now. Let's build another cell. Let's say we're going to build one now with copper. Now it's interesting, when you build the cell with copper, the hydrogen electrode ends up becoming the anode, and the copper electrode ends up becoming the cathode. And when we build it, we read a potential of 0.34 volts. Let's do a similar analysis to the one we did before, right? This is the cell diagram. Notice that in this case, On the left of that double bar indicating the salt bridge, we have the standard hydrogen electrode, but notice that it is in reverse. I have a platinum electrode to serve as depository for electrons, and I have hydrogen gas being oxidized into hydrogen ions. On the right side, I have copper 2 ions being reduced into copper. Let's write out the equations. So at the anode, I have the oxidation of hydrogen gas, losing electrons to become hydrogen ions. At the cathode, I have copper 2 ions getting electrons to become copper metal. Once more, I can add these. The electrons are going to cancel out, and I end up with the net equation for the whole reaction. Hydrogen gas reacting with copper 2 ions to produce copper metal and hydrogen ions. Now, how do we get the information we need from here? Well, like we said before, the potential of the cell should be the potential of the cathode minus the potential at the anode. In this case, the cathode would be the copper 2 converting to copper, and the anode would be the negative of the potential of hydrogen ions becoming hydrogen gas. Remember that we are at the anode, we're reversing the reaction, so we had to reverse the sign of the potential. Okay, the potential of the cell is 0.34 volts, and the potential of the hydrogen electrode is 0, because that's our reference. So this tells us that the potential for the copper 2 being converted to copper metal is 0.34 volts. Now that we have the standard reduction potentials for zinc and copper, let's go back to our original design of the galvanic cell. This was the one where we had zinc at the anode and copper at the cathode. And remember, the cell diagram looks like this. We have the anode on the left, the cathode on the right. Now let's see how that 1.10 voltage came out. Remember that the formula is that the potential of the cell will be the standard reduction potential at the cathode minus the standard potential at the anode. In this case, the cathode is the copper 2 being converted to copper, and the anode is the potential of zinc ions being converted to zinc. Remember, the standard potential is always for the reduction. We took care of the reversing of the reaction by putting the minus the potential at the anode in there. So according to the previous slides that we did, we know the copper electrode has a potential of 0.34, and the zinc electrode has a potential of negative 0.76. So when we add those up, we get 1.10 volts, which is exactly what the galvanic cell does. So that means that if we had a catalog or a list of all the different possible reduction potentials of different species, we can calculate what a given cell will have as its voltage. Here is a table that we will discuss in our next section. This is standard electrode potentials at 25 degrees for many different species. And what I'd like for you to do is take a look at it. We will begin our next class by discussing this table and then doing some practice exercises with it. All right. So until then, have a great evening.